All right, so hello everyone. I'm Norman Wildberger. We're here at the University of New South Wales. And today in this little course on probability and statistics, we'll talk about the total probability rule, another rule called Bayes' rule, and tree diagrams. All right, so I have to remind you of a few things about the setup so far. So we're talking about probability spaces. And that's a sample space, which is just a set. Usually we think of it as sort of outcomes of perhaps some experiment, plus a probability measure on that sample space. And the probability measure usually denoted P. All right, so we have a set S, which is rather general, and we have these various elements in S, say S1, S2, S3, and so on. And to each one of these we have a probability. So we have a little number P of S1, and the sum of all these, maybe PSI, sum of all the SIs in S, of the various probabilities, is equal to 1. So these are probabilities. Okay, that's what a probability space is. And then we talked about events. So an event is just a subset of a probability space. So we look at some subset, say E. That's a subset of S. That's what we call an event. Okay, and then the probability of that event is just the sum of all the probabilities of all its constituents. Okay, so an event E is just a subset of S, and we define the probability of E to be the sum of all the S's belonging to E of P of S. Okay, so that's the general setup. And now we have this idea of the independence of events. So maybe we have two different events. I'll write maybe A and B. Here's two other events. And we say that events A and B are independent. So what that meant, I remind you, is that the probability of A intersect B, so the intersection, there it is. So if you calculate the intersection, calculate the probability of that is just exactly equal to the probability of A times the probability of B. That's what we mean when we say that events A and B are independent. Okay, and we can actually extend this just a little bit while I'm talking about this. Let's extend it a little bit. We can extend this to more than two subsets. So for example, suppose we have say A, B, and C are all events inside our sample space. So we would say that the set A, B, and C of events, A, B, C, are mutually independent. So now we have three sets, not just two. Mutually independent means that, well, first of all, A and B are independent. So the probability of A intersect B equals the probability of A times the probability of B. And also A and C should be independent, which is this relation. And also that B and C should be independent, which is this relation. And then there's a third thing that we could ask, or I guess a fourth thing that we could ask, which is that the probability of the intersection is the product of all the probabilities. P of A times P of B times P of C. So all possible combinations of two events or three events, their intersection is just obtained by multiplying the probabilities of the individual events themselves. Okay, and for more than three sets, for example, let's say A1, A2, up to AK, all subsets of S, we can generalize this by saying that the set A1, A2, up to AK of events is mutually independent. Okay, how do we say the same kind of thing but capturing all of these possible relations all at once? We'll say it this way. We'll say if the probability of AI1 intersect AI2 intersect all the way up to AIL, say, is the product of the various probabilities AI1, probability AI2, all the way up to probability of AIL. For any subset, I1, I2, up to IL, a subset of the indices, the index set 1 through K. This is a sort of a flexible way of capturing all of these relations at once. All right, now let's remind you about conditional probabilities. So then we had this other notion of a conditional probability. All right, so again, the same diagram. We have a big set S, we have some subset A, we have some other subset B. These are events inside the probability space. Then the probability of A given B is defined, and we read it as the probability of A given B. And that was, by definition, the probability of the intersection divided by the probability of B. So when we want to look at probability of A given B, what we're doing is we're looking at really only just this part of the story. We're looking at what's happening in B and ignoring everything else. And we're comparing the probability of the intersection with the probability of all of B. So it's the ratio of this probability to the probability of B. That's the probability of A given B. All right, so effectively what you're doing is you're ignoring everything outside of B. Your whole world has shrunk from S to B. And then inside your B, you're asking what's the probability of A happening. So A is then represented only by this little portion. So you have to add up the probabilities there and divide by all the probability of B. So an obvious observation is that if A and B are independent, then this conditional probability simplifies. The probability of A given B becomes just the probability of A. Why? Well, it's simply a consequence of the fact that independence means that the probability of A intersect B is the probability of A times the probability of B. And then if we replace the numerator here with probability of A times the probability of B, then we cancel, we just get probability of A. So if A and B are independent, then the probability of A given B is the same as the probability of A. In fact, this is equivalent to it being independent. So you can think of the conditional probability as somehow, telling you a little bit about how not independent they are. Okay, so the first rule that we want to talk about today, the new rule, is called the total probability rule. And it's the situation where you have a sample space S, and it's partitioned. So it's partitioned, say, A1, A2, up to, say, AN. So suppose that A1, A2, up to AN is a partition of S. I remind you what that means is that these are subsets which together their union is all of S, and there's no overlap. All right, that's what partition means, just like I've drawn it here. They're completely disjoint, but together they form all of the space. Okay, and let's set, we need one more thing, and we'll suppose that B is an event in S. Okay, I only have the one color today, so here's B. All right, there's some other event B. Then the probability of B equals the sum from I equals 1 to n of the probability of B given AI times the probability of AI. So it's a sum of conditional probabilities, the probability of B given AI, times the actual probabilities of the events in the partition themselves. And we're summing from I equals 1 to n. So there's one such constituent for each of the partition elements. Okay, the proof is pretty simple. The proof is an observation that we can write B as B intersect A1 which would be that part of it there. Union B intersect A2, union all the way up to B intersect AN. And this is a disjoint union. In other words, all these pieces are completely separate. So the first one would have been that piece there. The second one, B intersect A2, well, that would have just been that part of it. B intersect the next one would be that part of it, and so on. All these pieces fit together to form B. Okay, so therefore the probability of B is the sum of all the probabilities of all the elements of B. So it's going to be the probability of this plus the probability of this all the way up to the probability of this. All these probabilities added up together, because these are all disjoint events. So it's the probability of B intersect A1 plus the probability of B intersect A2, and so on all the way up to the probability of B intersect AN. But what is the probability of B intersect A1? We can write that as the probability of B given AI, given A1, times the probability of A1. So this is the probability of B given A1 times the probability of A1. Just have a look at that. So remember, what is the conditional probability? It's defined to be the ratio of the intersection probability divided by the probability of the second piece. And so the intersection probability is the product of the conditional probability times the probability of the second component. That's an immediate consequence of this. If you just take this equation here and you solve for this thing, you get the probability of A intersect B is the probability of A given B times the probability of B. And we just do the same thing for all of these terms, all the way up to the last one. We get the probability of B given AN times the probability of AN. And that's what we're writing down here. That's just the same expression written in summation notation. All right, let's see how it looks in an example or two. All right, so let's say we're interested in deciding whether it really does rain more on weekends. Does it rain more on weekends is the question we're interested in. So maybe we perform an experiment. We're not going to take anybody else's word for it. We're going to make observations on our own for a year. And let's say that we decide that after a year of observation, we find that the probability of rain is R, okay, short form, R, on a work day. Workday will be represented by W, is, let's say, 0.2. So if it's a work day, there's a 1/5 chance of it raining. And let's also suppose that the probability of rain on weekend day, which we'll denote by H for staying at home, is 0.3. So maybe we find that, in fact, yes, in our year, it actually has rained. It's more likely to rain on a weekend than on a work day. So we've gathered this data. So now we can ask another question. What is the overall probability of rain on a random day? How do we put these two pieces together to figure out how likely is it to rain on a random day? All right, to answer this kind of question, it's useful to introduce what they call a tree diagram. Okay, a tree diagram is just a diagram that illustrates the various possibilities, usually read from left to right. Okay, so we introduce a tree diagram to represent this situation. Okay, so the first node will be whether it's a work day or a weekend day. So let's say W and H. This is the first possibility. So we're going to read from left to right. Okay? This represents a splitting of possibilities. If you choose a random day, what's the probability of that random day being a work day? The probability is 5 over 7 because there are, let's say, 5 working days out of 7. So we're going to ignore holidays and such things. And the probability of being a weekend day is 2 out of 7. Okay, and now we're going to split the tree into some more possibilities. Here's rain. So if it's a weekend day, it could either rain or it could not rain. And let's say rain if rain is R, not rain is, say, D for dry. Of course, that could also happen if it's not just a work day, but also a weekend day. It could rain or it could be dry. Now we're told that the probability of rain on a work day is 0.2. So the probability of getting to here, given that we're here, is 0.2. So I'm going to write 0.2 here. And that means that the probability of it being dry on a work day is 0.8. Just the 1 minus that one. So these are actually conditional probabilities. What we're really saying is that the probability of R given W is 0.2. And that the probability of it being dry, given that it's a work day, is 0.8. And similarly down here, the probability of it raining if it's a weekend day is, we said, 0.3. And so the probability of it being dry is 0.7. So there's 2 more conditional probabilities really appearing here. These numbers are also conditional probabilities. The probability of rain, given that it's a weekend day or a home day, is 0.3. And the probability of it being dry, given that it's a home day, is 0.7. Okay, what are we interested in here? The question that we asked is, what is the overall probability of rain on a random day? So we're asked, what is just the probability of rain? Well, this is a situation where the total probability rule comes in. The total probability rule in this case says that it's the sum of two terms, one corresponding to this way of reading the diagram of getting a rain outcome, and the other one is this way of getting a rain outcome. There are two possible ways that it could rain. It could either rain on a work day or on a home day. So the probability of R is, according to the total probability rule, the probability of R given W times the probability of W. That corresponds to one path, plus the probability of R given home day times the probability of home. And maybe I'll squeeze it over here. So therefore, the probability of rain is the conditional probability of rain given a work day is, we've said 0.2. So 0.2 times 5/7. And the other one is the conditional probability 0.3 times 2/7. And when we work that out, we get 0.2286. Somewhere between 0.2 and 0.3. A little bit closer to 0.2 because there's more work days than there are home days. So here is the total probability rule being applied to this situation, and you can see that it corresponds to finding all the ways that we can get the outcome that we're interested in, namely rain, from starting from this leftmost point and working our way along the tree, multiplying probabilities for each branch, and then adding them up. All right, so now we want to talk about Bayes' rule, which is sometimes more unintuitive application of the same circle of ideas. All right, so recall that this conditional probability is not symmetric. So its probability of A given B is certainly not, in general, equal to the probability of B given A. Okay, so here's the rule. We have the same diagram that we did previously. We have a partition A1, A2, up to AN. We have some subset B. We know the probability rule that we've just written down, but now we're going to write down another rule. So the setup is the same as before. If A1 through AN is a partition of S, and B is in S is an event, then for any J, the probability of AJ given B is the probability of B given AJ times the probability of AJ divided by the probability of B. That's not actually the usual form of it. The usual form is a little bit more complicated, and I'll write down the usual form. Has the same denominator, rather has the same numerator, but the denominator is replaced with the probability rule expression, the total probability rule, which is that the probability of B is equal to the sum from I equals 1 to n of the probability of B given AI times the probability of AI. So maybe I'll write it this way. That's the usual form of Bayes' rule. But sometimes it's a lot easier to remember if you remember it as being a combination of this thing with the probability rule that we've just established. How do we establish this thing? Well, this one is obvious from well, really the definitions of the conditional probabilities. So star follows from, well, the probability of AJ given B is by definition the probability of AJ intersect B divided by the probability of B. While the probability of B given AJ is, again, the probability of the intersection divided by the probability of the second one, AJ. So I think you can see that if you take this one here and you replace the probability of the intersection with this times this, then we get that the probability of AJ given B is the probability of B given AJ times the probability of AJ divided by the probability of B. That was the first rule that we saw up here. So that's the justification for this. And then to go from here to here, we're just replacing the probability B with this expression in the total probability rule. So in our diagram, what are we computing here? So here's A1, here's A2. These are all these different possible events partitioning our sample space. And we have our other subset B. This is an expression, or Bayes' rule is an expression for the probability of AJ. Somewhere here is say AJ. It's one of the partition elements. Could be any one. We're interested in what the probability of this thing is given that we're in B. So if we know we're in B, what's the probability of actually being in AJ? Okay. We know we're in B. What's the probability of actually being in AJ? Well, if we go back to this rainy weather day situation, let's see what it looks like since we have the situation here. So in the previous example, suppose we're interested in suppose that on a certain day it rains. Okay, the only thing about a certain day we know is that it rains. And now we're interested in deducing from this setup is to know what's the probability that that day happened to be, say, a weekend. What is the probability that this day was a weekend day? Weekend is home day. So we're asking what's the probability of being a home day given that it's a rainy day? It's a different kind of conditional probability than the ones we've been talking about before. The conditional probabilities that have appeared so far are the probabilities, what's the probability of it raining given it's a weekend day or given that it's a work day? Now we're asking a different kind of question, the probability of it being a home day given it's a rainy day. Well, according to the Bayes rule, in the simplified form, this is probability of the conditional probability that it rains given that it's a home day, so we reverse these things, times the probability of the home day, divided by the probability of the rainy day. Okay, but the full expression is the probability of rain given home times the probability of home divided by, well, the same thing that we've written here, the probability of rain given workday times the probability of workday plus the probability of rain given home times the probability of home. So this amounts to the probability of rain given home. We've seen what that is. That's this branch right here. It's 0.3. The probability of being a home day, it's a weekend day, is 2/7. And here's this number that we've already computed. It's it's 0.2 times 5/7 plus 0.3 times 2/7. Okay, which we've already figured out. We've already figured out that this was equal to 0.2286. And so the answer is 0.375, it turns out. So the probability that the random day was a weekend day is 0.375. All right, this kind of application, this rule, actually has quite a lot of interesting practical usages, especially related to medical testing and certain probabilities associated with testing positive for various medical tests, some of which are a little bit surprising and probably ought to be better known to the general population. So we're going to look at an example which is quite instructive, I think. So a medical example. Okay, first of all, a little bit of notation. If you take a test, a medical test is positive, just notationally, if you take a test for leukemia or something and it comes back positive, it doesn't mean that it's a good result. Okay? It means that the answer is yes. You have whatever it is that you were testing for. Okay? So test is positive means that, well, the disease is there. Okay, so we're clear on what positive means in this context. Okay, but tests for various things are not infallible. Okay, tests have a certain probability of being right, a certain small probability of being wrong. And it's this small probability of being wrong that has to be incorporated into your understanding of these medical tests. So we're going to look at an example. So we'll talk about some random disease. So first of all, a random person has disease D, so we don't really concern ourselves with what the disease is, just some disease, okay? So he either has a disease or not. And we'll denote those two outcomes by D. D means you have the disease. D complement means you don't have the disease. Okay. And let's say that we know suppose that 3% of the population has the disease. Okay, so 3% of the population has this disease. And now there's a certain test. The test is different, or the effectiveness of the test is slightly different depending on whether you actually have the disease or not. It's not a question of whether the test is right or wrong. It's a question of whether the test is right or wrong if you have the disease, and the question of whether the test is right or wrong if you don't have the disease. Yeah, so you take a test, and a certain test, a test for the disease D, is 99% sure of returning positive if the person has the disease. And 98% sure of correctly returning negative if they do not have it. All right, so this test is pretty good. 99% of the time, if you have the disease, the test will correctly identify that you do. 1% of the time it's wrong. On the other hand, if you don't have the disease, then 98% of the time the test is correct and will identify that you don't have the disease. So most of the time this is an effective test. Okay, so here are the various possibilities. There are, first of all, two possibilities. Either you have the disease or you don't. And the probabilities associated with that are just 0.03 and 0.97. Because we're just taking a random person from the population and asking, does this person have the disease or not? So there's a 3% chance of having the disease for a random person, a 97% chance of that person not having the disease. All right, we take this random person, perhaps it's you, okay, and we're going to apply the test to see whether you have the disease. So you take the test, you get your needle. What's likely to happen? Well, if you had the disease, we're not saying you do, but let's say you did. If you had the disease, you're either going to get a positive or a negative. Let's say yes or no. Okay, so yes means yes, you have the disease. What's the probability of that? Well, if you do have the disease, the test is 99% accurate. So there's a 0.99 probability of it correctly saying, yes, you have the disease. And a 0.01 probability of it being wrong and saying, no, you don't have the disease. Well, really, you do. That's what this information is up here. On the other hand, if you happen to not have the disease, there are still two possible outcomes. Yes, no. If you don't have the disease, the test correctly says you're okay, you don't have the disease, no, with probability 0.98. So we have to put a 0.98 down there. And we have to put a 0.02 up here because there's a 2% chance that the test is wrong. And then it tells you that you have the disease even though you don't. So this tree diagram represents the various possibilities that can come out when you take a random person, say you, and you apply this test to see whether you have this disease or not. Okay, what are we likely to be interested in? The interesting probability is, or the interesting question is, given a yes outcome, what is the probability of D? All right? That's actually what you're really interested in. You have this test, you think you're fine. The doctor says, I'm sorry, I have bad news. You've tested positive. You go, oh no, I've tested positive. The error looks like it's relatively small, 1%, 2%. But we'll shortly see that things are not at all so simple. Okay, Bayes' rule tells us something quite different, something unintuitive is happening. We're interested in the probability of disease given the yes. Okay, so how do we find that? Well, I guess we can probably squeeze it here. So the probability of disease given y is, according to the Bayes' rule, it's the probability of y given d times the probability of d divided by the probability of y. Okay, what are these various numbers? The probability of y given d. Probability of y given d, that's this conditional probability right here. Probability of y given d. So that's 0.99 times the probability of d. Probability of d is 0.03. And what is the probability of y? Well, that's given by the total probability rule. The total probability of y is the sum of the probability going this way to this y and the probability going this way to this y. Okay. So it's equal to the probability, maybe I'll write it down, probability of y given d times the probability of d plus the probability of y given d complement times the probability of d complement. And I know the tension is unbearable. What is the probability of us really having the disease? We have to do the computation. So this is, there's a 0.99 up at the top times 0.03, and on the bottom we have to multiply by these two chains. So there's a y given d, that's a 0.99 times 0.03, that's the same thing that appeared there. And then we have to add the other one, which is this 0.02, that's the probability of y given d complement, times 0.97. Now that turns out to be 0.605. It's roughly a 60% chance. So even though the test is relatively accurate, the fact that there's such a lot of people who don't have the disease skews the probabilities. So that even if you score positive, Bayes' rule is telling you that you don't need to panic entirely. There's a good chance that there's some error in the test. Your total chance of having the disease is actually still only 60% at this point. Right? So it's very important to understand this, because this is a situation that happens in practice quite a lot in medical situations. All right, next time we're going to go to random variables and start talking about the main objects of interest in probability theory and statistics. See you then.